Conservation momentum number 1. So we read the scenario. 4 cars on a track together. There's a dynamite charge. The charge goes off. The cars move. And one car moves off to the north. So in this case, we have an explosion. So we take note that this is an explosion. We know this is inelastic. In other words, kinetic energy is not conserved. We know that. So I'm going to set up my before and after situation. Before and after, we have north positive, south negative, north positive, south negative. So we have 4 cars, like so, identical. And the one that's going to move off to the north would be on this end. So we've got the dynamite charge in there. And then afterward, this one moves off in this direction. And so we know because of the law of conservation momentum, these guys must move off. Since these cars are identical, I expect that this one will be faster and this one will be slower. In fact, I would expect it to be 1/3 as fast. And I can check that later. We'll do the calculations to demonstrate it. So this velocity is 2.672 meters per second. So I've got my before and after diagrams. Now I'm going to do an inventory. Inventory, I have mass, which is 15,742 kilograms, which has 5 significant digits. And naming these, maybe we'll call this V1 and we'll call this V2. We know V1 is 2.672 meters per second, and that's with 4 digits. And we could call this M2 and this M1. So M2 is going to be 3 times 15,742 kilograms, and that'll have 5 significant digits as well. That number happens to be 47,226 kilograms. So we're looking for V2. What is that equal to? So most likely our significant digits are going to be 4 in the final answer. So what we know is the momentum before equals the momentum after. And before, we know the momentum is 0. Both of these are at rest. Afterward, we have the momentum of 1 plus the momentum of 2. So this is M1V1, and this is M2V2. So 0 is 15,742 times 2.672 plus 47,226 times V2. So 47,226 V2 is equal to negative 42,062.64, dividing both sides by 47,226. And we find that V2 is negative 0.890666 meters per second. That's the unrounded answer. And with significant digits, we go back here. So we've got 5 times 4, and we've got a 5. So this is going to yield a 4. So that's going to have 4 significant digits divided by 5 gives 4. So 4 significant digits is negative 0.8907 meters per second. So now I check my before and after diagrams, the inventory where I have my quantities. These are the quantities, the magnitudes, the directions, whether it's plus or minus, the units, and the significant digits. I have my formula, substituted correctly, did the calculation with the unrounded answer in units, and now I have the correct answer with significant digits, and the last thing is to box the answer, like so. Moving over the other side, to answer the following questions. Is the kinetic energy of the system conserved? Now, I took note of this in the beginning that I expect it not to be. But let's consider the kinetic energy. Is it conserved? Does the kinetic energy before equal the kinetic energy afterward? Well, let's take a look at the kinetic energy before. Kinetic energy is 1/2 mv squared. Velocity is 0 of all the objects, so the kinetic energy is 0. Is the kinetic energy 0 afterward? The important thing to remember here is that the v is squared. So even if this were a positive and a negative, it's not going to cancel out. All energies will be positive, calculated this way. So we know the kinetic energy is going to be greater than 0. Since the kinetic energy beginning is 0, and the kinetic energy final is greater than 0, kinetic energy is not conserved. What impulse does the single car receive? So the first thing I'm going to do is order my thoughts. Impulse is change in momentum, is m delta v equals f delta t. So we're looking for the impulse. Well, do we know the change in momentum of the single car? Well, we know the mass, and we know the velocity it undergoes. We don't just know the change in momentum, and we don't know anything about the forces or the times involved. So we have the mass, which is 15,742. Change in velocity was 2.672 because it went from rest to this speed. And we actually did this math here, which is 42,062.64. 4 significant digits. That's going to be 4.206 times 10 to the 4th Newton seconds, and that will be the impulse. See if that makes sense. Impulse is a vector, so in this case here, its momentum changed in this direction, so it did receive a positive impulse. Now, what impulse do the remaining cars receive, or does the what impulse do the remaining cars receive? Well, let's consider this. For every action, there's an equal and opposite reaction. They exert equal and opposite forces on each other for the same amount of time, and that is F delta t. So the change in momentum must be equal, and therefore the impulses are equal. Now, of course, we know in an explosion, the momentum gained by one object in the positive direction is offset by the momentum in the negative direction, so they should be equal in magnitude and opposite in direction. So if the one received this, then the impulse of the 3 cars should be opposite that, negative 4.206 times 10 to the 4th Newton seconds for all 3. Per car, it would be this divided by 3, or 14,020.87 Newton seconds for each, which would be 1.402 times 10 to the 4th Newton seconds. So 2 answers here, actually negative. Remember, it's negative because it's the other direction. And that's how we tackle this quiz.